I thank the organizers of ABSCON and also IIT Hyderabad for coordinating this ABSCON conference here. Nice campus. So I am from Indian Institute of Space Science and Technology, and I'm going to talk about some of the work done by my master student along with my PhD student. Master student is Mayank. He has joined for PhD in IIT Kharagpur, so he couldn't join. So I'm presenting on their behalf. So this is something that we have been working on, integrated MEMS, electronics integrated sensors, in which we try to integrate MEMS and FETs. I'll give a brief overview of what it is. And our institute is a unique institute. It's the only institute under Department of Space. And we work on UG, PG, and PhD program related to space science and technology. We have undergrads and PG, 15 PG programs in different areas. So those who are interested, you can go into it and specifically talking to students. Coming to MEMS, we know that we have a lot of advantages like micro electromechanical systems. It has all the advantage of electronics, miniaturization that you know, and also parallel sensors can be made. Sensors can be of different nature but fabricated together. Variability will be very less. Those are the typical advantage of MEMS. And at IST in my group, we are ours MEMS Sensor Systems group. We work on different types of sensors, right from the sensor transaction schemes, like the conventional resistive transaction, like piezoresistive, piezoelectric. We work on sensors. We work on energy harvesters. We also work on integrated CMOS MEMS devices, wherein we try to integrate electronics, sensors, and the VLSI together. We work on polymer MEMS, ceramic MEMS, and these days we have also started working on 2D MEMS. And energy harvesters, I was on the right side on the corner. So that is actually that we are recently developed with piezoelectric devices. So this is the typical soy MEMS process done with the aluminum nitride piezoelectric layers. And now coming to today's talk, I would like to touch upon what is the micro nano force sensing, how it is done, what is the concept of the suspended body FET, and the device architecture with what is this double gate MoS2 FET with a hybrid transduction, and the configuration in circuit and its results and discussion. Now coming to force sensors have a lot of applications, right from industrial robotics. I am sure you would have got a lot of information by the two plenary talks which happened day before yesterday and yesterday, as well as today. And biomedical cell manipulation, we really require minute measurements of forces. Material science and nanotechnology, that anybody who worked on atomic force microscope, they will know about the requirement of force measurement. There are other requirements also where you really require microscale force measurements. There are some standard transducers available, which is shown on the right side. They are slightly bulky, which is actually capacitive as well as piezoresistive. We are just trying to address some of their disadvantages. Now coming to typically MEMS, what we try to understand, what do we try to know before we develop these sensors? So we basically would like to know the mechanics of microsystems. We also would like to know how to transduce. That just means this converting from the mechanical domain to electrical domain. And these days we talk about optical as well. So it can be typically capacitive, like a capacitor changing its capacitance with moving electrodes. And it can be piezoresistive, where you have resistances kept in high stress regions. So that means we need to know how much is the displacement of those structures. And we also would like to know what is the stress. If you know these two things and get a range of these values, then we will be able to come up with some new techniques to measure them. So this is the idea, need to know the mechanical behavior as well as their viable transaction schemes. Now, coming to the transaction schemes, the conventional ones, which we know, the conventional pressure sensor, we will know it is pressure piezoresistive, but it is prone to drift to temperature variations because it's resistive. Capacitive, if you need large, good signal to noise ratio, the capacitance sensors are typically big. So large sensor footprint is a disadvantage. Piezoelectric, it's not suitable for DC kind of measurements. You cannot go to very small variations. It is good for dynamic variations of forces. And also temperature variations also affects the piezoresistive. So capacitive seems to be outperforming both of them generally in commercial sensing as well. But there are other applications where piezoelectric as well as piezoresistive is still in use. So that means if I talk in context of force sensing, force converted to delta C, that is, you should have a C to V converter and an amplifier. This is a typical architecture. So C to V converter is something that is the key part which actually adds to the noise. So if you really want to increase the signal to noise ratio, at the same time keep the sensor footprint small, C to V has to be completely removed. So that's the idea or motivation with which we come up with the new sensor type of sensors, which has some idea already in the literature earlier days, the suspended gate transistors. So you can see here that the transistor is, this is a conventional transistor, but the gate is suspended. The gate is away from the channel. So it's equivalently, we can think about two capacitors in series, one the moving capacitance and the other is the variable capacitance. So with this, we can measure the change in current with the conventional current equation written below. Now, so this is how it's actually, now you have your micro sensor. It can be force, it can be anything. We work on other applications like accelerometers, which I've shown on the right. And you directly get the delta I, and then that can be part of a differential amplifier, or it can be part of any amplifier stages which is coming up later on. So this itself, MEMS-FET based transaction, is really a paradigm shift in terms of bringing an amplifier to work like a transducer. So inherent amplification and high signal to noise ratio. And you have a very good scope of CMOS MEMS integration. That means on-chip integrated sensors without much of a fiddling. You don't need a large area capacitor to be integrated. Challenges related to MEMS and CMOS, those kind of things can be completely waived off. That is advantage. So right on the right, you can see a closed loop FET MEMS accelerometer, which was done by my PhD student earlier. And this is also patented. So this is with multiple combs acting as actuator. And so it will bring the gate into the nominal position. So this is not out of body moment. This is in plane moment of the capacitive accelerometer. And so, but then what are the challenges? It looks very simple, but there are challenges. So FET being a very good, the entire CMOS industry is trying to scale down transistors. When we scale down the lateral dimensions, we also try to scale down the transistor gate area of the thickness of the gate dielectric also, so that the gate coupling increases. But here we are doing the other way around. We are bringing the gate away. So that means all the short channel effects that you have seen in small transistors, you will start seeing in the bigger transistors. So it's like pseudo short channel effects. That's one disadvantage of such things. So we had come up earlier with ideas of using some non-conventional, non-planar structures like U-channel transistors, silicon-based transistors to solve this, so that electrostatics of the transistors has been modulated. So, but then challenge is there in fabricating these U-channel transistors in the current scenario. CMOS MEMS fabrication, because again, these U-channel transistors are very difficult. Also, though we have done a lot of work, we're still continuing on silicon MEMS, and we recently developed some interest towards 2D. 2D, there are two reasons. It's not just that we are working on 2D and we wanted to try SGFET also in 2D. 2D being a ultra-thin body MOSFET, like the advantage we see in ultra-thin body MOSFETs, with short channel effects being mitigated, you can get the same advantage if you use 2D materials. So that is why in our group, we are working on gas sensors and other MEMS devices using 2D. So we were able to develop some large area 2D in our lab, that is MoS2. And this is a pattern MoS2 transistors with the TLM structures. So that is the idea. So we will have the suspended gate of the structure. This is one idea of suspended gate MOSFETs with 2D. Now, are we really happy with the suspended gate, or can we do something else also? That is the motivation of what we did today. So this is the suspended gate, but then the MoS2 being, even though it is very flexible, we are making it sitting on the substrate. What if we take it to the suspended structure? So that is actually the suspended body FET. The body is suspended. We get all advantage for the suspended. Usually in even MoS2 characterization, those who have worked on transistors, they know that the interface quality is degraded if you are with the substrate. They suspend it. So we suspend that structure with the MEMS device, and then we can actually measure the change in capacitance. Okay, so that then what we can see is that here, unlike the accelerometer, we can see that there is a curvature, and hence the capacitance variation is happening. So that means there is still a room for changing that idea, that we can make it flat. Secondly, a change in capacitance in the perpendicular direction is always inversely proportional to the displacement, because 1/d dependence. So non-linearity will come for the sensor. So we came with an idea that why don't we make, now that we can make it suspended, MoS2 can be suspended. Now the MoS2 is also having very well-known property of strain engineering. MoS2's piezoresistance property is well-known, well-reported, but with different values reported in literature. So we came up with the idea that we could actually integrate a hybrid transition scheme in which the suspended body transistor sits in the center region, which is a rigid body, and the flexible regions, in the high stress regions, we locate the piezoresistive MoS2. It can be in the transistor configuration. Right now, we have done in the resistive configuration. And the structure also has to be very flexible. Instead of silicon, we use parallel C as a MEMS structural layer. And we have some strength in the parallel MEMS in our group. So the device is finally, this is the architecture of the device. So we have something like 7 levels of lithography to realize the structure. And this is ultimately going to be connected in common source configuration with the resistor as the piezoresistor as the load resistor, and transistors whose current also resistor as well as current changes, because of which with certain optimization one can get the linearity out of the sensor. And there are different ways in which we can design. So design thinking depends on what you want. So natural frequency is something, spring constant in sensitivity, pull-in voltage is something well-known in capacitive devices. If you make larger structures, pull-in is a problem. If you make smaller, sensitivities go down. So that is actually the trade-offs. We work a lot on that. And large area of the proof mass, so well discussed in the paper. Due to time constraints, I'll skip this off. And so now coming to the simulation methodology that we run, we did mostly using the COMSOL multiphysics, but at the same time, we have used FEM software, which is used for the MEMS devices. We use Coventerware for most of the electromechanical part. We also use it the same in the MEMS as well, in the COMSOL as well. So the suspended body is structure is made in the multiphysics module of COMSOL. So it has a semiconductor module in which you can do that. You can take the moving area mesh from the MEMS structures to make this suspended body device work exactly like moving structures and do the simulations. And with an LUT approach, we can take it to the circuit simulation. That's what we did. And this is the characteristics of MOSFET under different gate conditions. And in fact, we have also done the, modeling of this using the conventional techniques used in MoS2 devices. Now, coming to the simulation of the electromechanical devices, we did with the displacement of the structure. We can see that the center region is a real rigid body movement. It's parallelly moving. And you can see that the edges, which is having the high stress regions, they are still under stress. And this is the stress profile of the structure. We can see that the stress is maxima at the near the anchor region, and the center regions are not stressed. So the parallel movement of the transistor body is ensured. And we can see that the delta R by R for the piezoresistance measurement, and certain modeling is also done in these aspects. And then we did the modeling of MoS2 with the double gate MOSFET architecture. We modified the model a little bit, starting from the Poisson's equation to finally the device current equation. And this is how the drain current with the model and simulations. And this is the results of different forces. And we can see that the IDVD characteristics, we are showing with air gap, we can see the current changes really. But we can, as I predicted in the beginning, it is going to be nonlinear. Now with the resistor attached to it, we can see that with certain optimization of the resistor values, here comes a lot of optimization with regards to the bias voltage that you can apply, because it should not cross the pull-in. At the same time, transistor has to be biased in above threshold. At the same time, gate overdrive voltage should be sufficient. Resistor value should ensure the VG minus VT to be sufficient, so that transistor is in the saturation. So those kind of optimization, we could get that V out, which is something like 1 microvolt per nanonewton of sensing. And with this work, we were able to get much better sensitivity as reported earlier. In our group with the silicon, with a U-channel SGFET, that device is very good, but complexity is there. So with this, I would conclude my talk. So we were able to develop. Now the fabrication is still going on. And I would like to thank my students who have done this work in our group, and also ISRO and our funding agencies, wherein we have got a lot of good support, mentors and collaborators. Thank you.